Let's solve this problem together step by step. And I want you to notice how beautifully similar triangles help us find the area of the square without using any complicated formulas. We are given a right triangle PQR, where the two legs are QR equals 6 and PR equals 8, and the hypotenuse PQ equals 10. Inside this right triangle, there is an inscribed square ABCD, and we are told to let the side length of the square be S. Since it is a square, all four sides are equal, so AB equals, BC equals, CD equals, DA equals S. That gives us one unknown, and our entire goal is to find the value of S, because once we know the side of the square, finding its area will be very easy. Before we move ahead, remember that the area of a square is simply side multiplied by side, or side squared. So everything we do from now on is focused on finding the value of S. Also, if you're enjoying learning mathematics this way, where every single step actually makes sense instead of just memorizing formulas, make sure to like this video, subscribe to the channel, and let me know your answer, any doubts in the comments, because I'd really love to hear from you. Now, let's continue. The next important observation is that the entire hypotenuse PQ is divided into 3 smaller line segments. Those segments are QA, then AB, and finally BP. Since these 3 segments together make the complete hypotenuse, we can write PQ equals QA plus AB plus BP. We already know that the total hypotenuse PQ is 10, and we also know that AB is one side of the square, so AB equals S. That means if we can express QA and BP in terms of S, then we can substitute everything into this equation and solve for the side length of the square. So the question now becomes, how do we find QA and BP? This is exactly where similar triangles come into the picture. Let's look at the upper smaller triangle first, which is triangle QDA. This triangle shares the same angles as the large right triangle PQR. Since corresponding angles are equal, these two triangles are similar. Remember the property of similar triangles. Whenever two triangles are similar, the ratios of their corresponding sides are equal. That means we can compare matching sides and create proportions. In this case, the leg adjacent to angle phi divided by the leg opposite, angle phi in the smaller triangle, corresponds to the same ratio in the larger triangle. So we write QA divided by AD equals QR divided by PR. Now, let's substitute the known values. AD is one side of the square, so it equals S. QR is 6, and PR is 8. Therefore, we get QA divided by S equals 6 divided by 8. Now let's simplify 6 divided by 8 first. Both numbers are divisible by 2, so this becomes 3 divided by 4. We now have QA divided by S equals 3 divided by 4. To isolate QA, multiply both sides by S. On the left side, the S in the denominator cancels with the S. We multiply by, leaving only QA. On the right side, we get 3S divided by 4. Therefore, QA equals 3S divided by 4. Great. We now have our first segment written completely in terms of the side length of the square. Next, let's do exactly the same thing for the lower, smaller triangle, triangle BCP. Once again, this smaller triangle shares angles with the large right triangle, so these two triangles are also similar. And just like before, corresponding side ratios must be equal. Here we write B P divided by BC equals PR divided by QR. Again, substitute the known values. BC is one side of the square, so it equals S. PR is 8, and QR is 6. This gives us BP divided by S equals 8 divided by 6. Now simplify 8 divided by 6 by dividing both numerator and denominator by 2. That becomes 4 divided by 3. So we now have BP divided by S equals 4 divided by 3. Multiply both sides by S to isolate BP. The S on the left cancels, leaving BP, and on the right, we obtain 4S divided by 3. Therefore, BP equals 4S divided by 3. Now we have expressions for both unknown segments. QA equals 3S divided by 4, and BP equals 4S divided by 3. Notice how similar triangles allowed us to replace unknown lengths with expressions involving only S. This is the key idea that unlocks the whole problem. Now let's substitute these expressions back into our earlier equation for the hypotenuse. Remember, QA plus AB plus BP equals 10. Replacing each segment with its expression gives us 3S divided by 4 plus S plus 4S divided by 3 equals 10. Now we need to combine these three terms, but before we can add fractions, they must have the same denominator. The denominators are 4, 1, and 3. The least common denominator is 12. So let's rewrite every term with denominator 12. 3S divided by 4 becomes 9S divided by 12 because we multiply both numerator and denominator by 3. The middle term S can be written as 12S divided by 12 because multiplying by 12 divided by 12 does not change its value. Finally, 4S divided by 3 becomes 16S divided by 12 because we multiply numerator and denominator by 4. Now, all three fractions have the same denominator, so adding them is easy. 9S plus 12S plus 16S equals 37S. Therefore, we get 37S divided by 12 equals 10. To solve for S, we remove the denominator by multiplying both sides by 12. On the left, the 12 cancels with the denominator, leaving 37S. On the right, 10 multiplied by 12 equals 120. So we now have 37S equals 120. Finally, divide both sides by 37. That gives us S equals 120 divided by 37. Excellent. We have successfully found the side length of the square. But the problem is asking for the area of the square, not just its side length. So, now we use the area formula we discussed at the beginning. The area of a square equals side squared. Therefore, the area equals the quantity 120 divided by 37 all squared. When squaring a fraction, remember that we square the numerator and the denominator separately. 120 squared equals 14,400, and 37 squared equals 1,369. Therefore, the exact area of the inscribed square is 14,400 divided by 1,369. If we convert this fraction into a decimal, we get approximately 10.52 square units, and that is our final answer. Notice that every step followed naturally from the previous one. We first introduced the unknown side, then used similar triangles to express the missing segments, substituted everything into the hypotenuse equation, solved for the side length, and finally squared it to obtain the area. That's a beautiful example of how geometry, proportions, and algebra work together to solve what first looks like a difficult problem. If this explanation helped you understand the logic instead of just memorizing the solution, don't forget to like this video, subscribe for more mathematics lessons just like this one, and leave a comment telling me which step made the most sense to you or what kind of problem you'd like to solve next.